Welcome to Lesson 2-3. This section is called Polynomial Functions of Higher Degree with Modeling. Here are your learning targets, and our focus in this lesson will be on polynomials that have degree 3 or 4, and we call those cubic and quartic polynomials. And we've talked a lot about end behavior and how to analyze different polynomial equations. And the end behavior is a description of what's happening to the y values or the outputs of the function as x approaches positive or negative infinity. And it turns out that if we can just look at some of our basic functions, our y equals x and y equals negative x, y equals x squared and negative x squared, if we just remember what goes on in the end behavior of those four functions, that actually describes the end behavior of all polynomial functions by just looking at their leading coefficients and the power of the polynomial. So let's take a look at how we can use that. Here's a table to help you remember what the end behavior will look like. So for example, let's say we have an even-powered polynomial, something like y equals x squared, and it has a positive coefficient. So we might have a graph that looks something like this. Okay, that tells us that the limit as x goes to negative infinity, so as x goes to the left, the output, the y values of the function, are going to positive infinity. And likewise, as x goes to positive infinity, the function is also going to positive infinity. Well, what happens if we have a negative coefficient? We still have an even power, but what happens when that coefficient is negative? So say we had negative x squared. Well, that function graphs like this, very similar to the one above, except it's reflected over the x-axis. So this time, both of the limits, the end behaviors, are going to negative infinity. How about an odd power? What if we had a cubic function like y equal x to the third? As long as the coefficient in front of the leading term is positive, that's how it graphs. So we can see that as x goes to negative infinity, the function follows, and as x goes to positive infinity, the y values also go to positive infinity. But then when we have a negative coefficient, remember that's just going to flip everything across the x-axis, so it'll look like this. And we get, as the limit goes to negative infinity, the function goes to positive infinity, and as the function goes to, as x goes to positive infinity, the function goes to negative infinity. So this will be the case for all of our functions. We can generalize this, whether it's x squared or x to the fourth or sixth or eighth or any other even power. The end behavior is the same. So let's do some examples and see if we can use this to help us. Describe the end behavior of the polynomial using limit notation. So in this one, we have an even power and a positive coefficient. So we know that will be up here in our first quadrant, top left, even power, positive coefficient. So our end behavior, both of them should go to positive infinity. In example B, we have an odd power and a negative coefficient. So odd power, negative coefficient, that's down here. So our end behavior should be as x goes to negative infinity, we'll go to positive infinity, and as x goes to positive infinity, we will go to negative infinity. So that's how you're going to use that table to help you describe the end behavior of any polynomial function. The zeros of a function are where it crosses the x-axis, also called the x-intercepts, and they are the values that make the function equal to 0. We can find those algebraically. We've been doing that by factoring. So here's an example where we're going to find the zeros algebraically, and we will look at what the graph of those looks like. So in our first example, we have x cubed minus 16x. Well, these have a common factor of x that we can take out. And then you should recognize x squared minus 16 as a difference of two squares. And then to actually find the zeros, you have to set each of those values equal to 0. And you will get x equals 0, x equals negative 4, and x equals 4. And then to support that graphically, I went ahead and graphed this on the calculator, and it looks like this. You can see that we have a 0 at 0, 1 at negative 4, and 1 at positive 4. Example B, again, we have a common factor of x that we can take out. And then you should be able to factor this, the factors of 6 that differ by 1, are 3 and 2. And then setting each factor equal to 0, we get x equals 0, x equals 3, and x equals negative 2. And then here is the graph that supports that as well. So sometimes we have factors that are repeated. This is called multiplicity, and multiplicity is just the number of times that factor occurs when we have a factored polynomial. So here we have a couple of examples of factored polynomials, and our directions say to list the zeros and state their multiplicity. And then we'll graph those and see what we notice. Well, we have a 0. If we set each of these equal to 0, x equals 0 is one of our factors. It has multiplicity 1. And then x equals 3 has multiplicity 2. See if we can get that to show up. There it is. And if we graph that, here's the graph of what we get. I'll talk about the graph a little bit more in just a minute. Over here on the right, for example B, x equals negative 1 has multiplicity 1. X equals 2 has multiplicity 2, and x equals 4 has multiplicity 3, and here is its graph. So one of the things that you might notice when we have odd multiplicity, look at when we have odd multiplicity. Over here we have negative 1 and then positive 4. Whenever we have odd multiplicity, it crosses the x-axis. When we have even multiplicity, it does not cross the x-axis. It just touches the x-axis. So that will also help us graph some of these polynomial functions. If we don't have a calculator, we know what it will look like. So let's see an example here. We have this function, f of x equals x to the fourth minus 25x squared. We're going to state the degree, and we're going to list the zeros of the polynomial function. We're going to state the multiplicity, and state whether it crosses the x-axis, sketch the function using the end behavior and the zero. So we're going to put this all together. Our degree here is 4. Okay, it's the highest exponent. And for our zeros in multiplicity, we need to factor this. And these two factors share a common factor of x squared, so we want to factor out the x squared, which would leave us with x squared minus 25, and then that is a difference of squares. Now when we set those equal to 0, we get x equal to 0 has multiplicity 2, x equals 5 has multiplicity 1, and x equals negative 5 has multiplicity 1. So remember the odd multiplicities, we will cross the x-axis, so at x equals 5 and negative 5, we will cross the x-axis. But at x equals 0, it's just going to touch the axis. So we'll keep that in mind as we do our sketch. Lastly, let's figure out our end behavior. Okay, this is an even degreed polynomial, and it has a positive coefficient. So we have an even power, a positive coefficient. So that'll be just like y equals x squared. So our end behavior, both limits, should go to positive infinity at the ends of the graph. So let's go ahead and sketch this thing and see what it looks like. So we want to make sure that we have our end behaviors both going to positive infinity. At x equals 0, it does not cross the axis, but at x equals negative 5 and positive 5, it does cross the axis. So there's a rough sketch of what that might look like. Here's another example. See if you can try this one on your own. Pause the video, and then I'll give you the answers when you come back. All right, let's take a look. This one, because we have a repeated factor here, this is like an x squared times an x, so our degree would be 3. Our zeros in multiplicity, we have a 0 at x equals 2, it has multiplicity 1, and a 0 at x equals negative 7, it has multiplicity 2. So the one with multiplicity 1 will cross the x-axis. At negative 7, we're not going to cross the x-axis. Our end behavior, we have an odd power and a negative coefficient. Odd power, negative coefficient. So that should tell us the limit, our end behavior as x goes to negative infinity will go to positive infinity. And the limit of the function as x goes to positive infinity will go to negative infinity. So let's go ahead and sketch this one. And we're going to have points at x equals negative 7 and x equals 2. And so our end behavior as x goes to negative infinity will go to plus infinity. It's just going to touch at x equals negative 7 because that is an even multiplicity. But at x equal 2 it will cross the axis, and then that will go down to negative infinity. Lastly, we want to be able to use our regression functions on our calculator to fit curves that follow data. Excuse me. So what I've done is I went ahead and put in the x values in list 1 and the y values in list 2. And I calculated the cubic regression. And on your calculator, I'll just show you what this looks like. When you go in here to your stat function on your calculator, and calculate is off to the right, you want to do, the first one is cubic regression, which on my calculator is option 6. And the second problem is the quartic regression, which is option 7. So I've put that data in there. And here's what I came up with for my cubic regression equation. So it gives you the form y equals ax cubed plus bx squared plus cx plus d. And then it gives you each of your coefficients for those terms. So make sure you're able to plug those into your calculators and find either the cubic or quartic regression. Here's the quartic regression answer. And if you have any trouble with that on your calculator, let me know when I see you in class next time. That's all for this lesson.